So this slide we see here is not exactly something. This isn't exactly the way I presented things, but I guess this is to review. We've seen this. Maybe I called it balance law, or this conservation law for the binormal curvature flow. If we have a smooth solution to the binormal curvature flow, and we let it act on a test function in the natural way, we integrate the test function over the curve gamma, and then we differentiate that with respect to time. Then we get this identity. And then there's a rather similar looking identity for the Euler equations. And so I kind of sketched a formal argument that involved using the Biot-Savart law, doing a sort of a Taylor expansion of the. So we use the Biot-Savart law to approximate the velocity generated by a smooth curve, but by vorticity concentrated in epsilon2 around a smooth curve. And we do a Taylor expansion of the curve at a point, and then that gives rise to that at least formally gives rise to this binormal curvature flow. I claim here that the similarity between these two formulas, formula 1 and formula 2, can be viewed as another formal argument in favor of the conjecture that, here's the conjecture, I think. The conjecture is that there exist solutions of the Euler equation for which the vorticity follows a trajectory given by a solution of this binormal curvature flow. So in other words, given a smooth, closed, non-self-intersecting binormal curvature flow in 3 dimensions, there exist solutions of the Euler equations rescaled in time with this logarithmic factor, such that, and so these equations say that the vorticity is a vector valued quantity. I can naturally take its dot product with a vector field script phi, and that should converge to the integral. So at time t, rescaled time t, that will converge to the integral of phi around of the vector field phi around the curve gamma, and then the energy associated with the curve, the kinetic energy, u squared, is of course a scalar quantity, a non-negative scalar quantity. And so it's natural to multiply that by a function rather than a vector field, a non-script phi. And after rescaling by this to get rid of the logarithmic divergence, this should converge to the integral of the scalar function around the curve gamma, just with respect to arguments. Okay, and so this is one formulation of the vortex filament conjecture, that given a smooth binormal curvature flow, there exist solutions of the Euler equation for which the energy and vorticity concentrate around that binormal curvature flow. Okay, and so what we did, actually here's a remark. So this conjecture has an analog in higher dimensions. And so then you would just replace the Euler equations in R3 by the Euler equations in R capital N, where N is greater than or equal to 4, for example. And then the analog of so then the same sort of formal arguments tell us to expect the vorticity should be concentrated around a codimension 2 submanifold. So a 2-dimensional submanifold of R4, for example. And then the law of motion, that is the higher dimensional analog of the binormal curvature flow, is the following. If I have to say a 2-dimensional submanifold in R4, or an n minus 2-dimensional manifold in Rn, well then at every point in the manifold there's a 2-dimensional normal, a normal space, an n minus 2-dimensional tangent space, and a 2-dimensional normal space. There's also a mean curvature vector, which will be a vector in the 2-dimensional normal space. And if the submanifold is oriented, then I can define, I can give a consistent sense to this operator I've written, script J. This would be a rotation by 90 degrees in the normal space. And by pi over 2, and I say pi over 2 in the positive direction, where positive is specified using the orientation. Okay, and so the analog of binomial, so binomial curvature says look at the mean curvature vector, rotate by 90 degrees. We just do exactly the same thing in higher dimensions. We look at the mean curvature vector lying in the 2-dimensional normal space, rotate by 90 degrees. This is called the skew mean curvature flow. And the same formal arguments that say that, the Euler equations, and actually the same is true for Gross-Pityevsky, the Euler equations and Gross-Pityevsky should have solutions with vorticity concentrating around a binomial curvature flow in 3 dimensions, would say there should be solutions in capital N dimensions with vorticity and energy concentrating around a skew mean curvature flow. Okay, and so all of the theory I'm discussing for weak solutions of the binomial curvature flow, in principle, one can ask about the extent to which the same theory can be developed in higher dimensions, and this is largely open. So it's a question that is interesting for me. Let's say, I'm not sure who else cares about it. Okay, and then local existence of this skew mean curvature flow in higher dimensions was proved recently by Chong Song and Xiamen. Okay, so then, so I'm going to discuss weak solutions to binomial curvature flow. This is work of myself with Didier Smets, and we discussed some of the motivations. Let's see, and so what I was talking about was the notion of an oriented varifold, which is sort of the so the idea of a weak solution is we want to basically ask what happens if we assume only essentially only this identity plus a little bit extra. So we look for a class of solutions that are characterized by this, and we ask, what can you prove about that? Because if I look at these two at identities of 1 and 2, and I imagine passing the limits from equation 1 to get equation 2, well, I won't have this pointwise PDE gamma sub t equals gamma SS, etc. I won't have that. All I would know about the limit of equation 1 is equation 2. And so it's useful from the point of view of Euler to ask, what does this actually tell us? Okay, and so then I started by introducing the notion of oriented varifolds, which here they are. And so I want to view these as a class of generalized surfaces, generalized curves in R3. And so an oriented varifold is a Radon measure on R3 cross S2. And the basic example is here. If I have a closed Lipschitz curve gamma, then, no, it's the basic example is here. If I have a Lipschitz curve gamma, so a map from S1 into R3, whose Lipschitz continuous, then I can define a associated varifold V sub gamma, the corresponding varifold, just in this way. So to define a measure on R3 cross S2, it suffices to specify how it integrate functions on R3 cross S2 against that measure. And so I define the integral of a function f on this product space against V gamma to be, well, what do? I integrate over the, essentially I'm looking at the image of the curve. So given this gamma, I can look at the map that takes S1 into the curve in R3 cross S2, given by the argument of this map here. So I'm gamma of S with the associated tangent vectors, right? So I have a natural curve in R3 cross S1, and I look at the push forward by that map of Lebesgue measure, essentially. Okay, so this is that's a natural example. That's the canonical example of a oriented varifold. The interpretation more generally, and this is literally true in the context of the above example. The interpretation is that the varifold V, the measure of the set A cross B, for example, is the length of the set of points in A whose tangent belongs to B. Okay. And I didn't talk about this last time, so let me do it up here. So this is easy, but I want to go over slowly so it sinks in. So here's the definition. An oriented varifold is closed. Let's call it V if sorry. Okay, so when I write this, X is always representing a point in R3 and C is always a point in S2, the tangent vector. Okay, let's say that. So this is the definition for closed. And remember, so let's go back to the Lipschitz curve to recall. For gamma S1 to R3, we have a map gamma whose parameterized by S1 is of course a closed curve, right? Because it's parameterized by map from the circle. And so the definition of V gamma is, well, I just integrate this thing around the curve. So gradient G at gamma of S dot gamma prime of S. I think I wrote it this way. Okay, these cancel. And this is 0 just because we're iterating a vector field around we're iterating a conservative vector field, a gradient vector field around a closed curve. And so the fact that this is 0 because the curve is closed. And if I had instead of a gamma, who was parameterized by interval, then it should be gamma at one endpoint minus gamma at the other endpoint. Sorry, G at one endpoint minus G at the other endpoint. So, and so this is, this conditions, this vanishing of this integral, of course, tells us that the curve is closed. And so we just take that as the definition of closed for this more general object. And so that's what was written here. And this is this example. I just wanted to do it a little more slowly. So we see it like this. Okay, and so so we say a variable is closed if it satisfies this for all test functions G, and the motivation is given in red. And then I think I said this last time. An integral varifold is one who is a sum of varifolds associated with Lipschitz curves, the linear combination. Okay, let me give an example of an Orion varifold who is not integral, just so we have some sense of what they're good for. Well, here are two examples. So one is, suppose I have a vector field U, and let omega be its the associated vorticity. So I want to think of U as being a velocity. I want to think of omega as being the vorticity. Then I can define a varifold associated to omega just in the following way. I would this is the so essentially this mimics the definition of the varifold associated to a smooth curve, except that omega is no longer in this case a constant on a curve. It's an L1. It's an L1 vector field. Okay, and so then, for example, so the integral of f of x dot c dv omega would be, or let's call this phi of x dot omega of x dx, for example. And so, but here, when I write it this way, I'm somehow thinking of it as a kind of a generalized geometric object. And so we can see that, note that v omega is closed. Because if phi is a gradient vector field, I can write this expression. I can enumerate my parts, and I will get a gradient of, I'll get a divergence of omega, which is 0 because omega is equal. Okay, so that's one example. Here's another example. Let's make this smaller. Okay, let me draw a picture of this next example. What it looks like is, well, you can see here alpha is a parameter. So we're looking at this example. Alpha and R are parameters. And so what this is if I look at the first two components, the x and y components, this just describes a circle of radius R around the in the xy plane, and then the last component is just moving up with constant velocity along the z-axis. And so and I guess I've chosen R and alpha. I've written this in such a way that we have an arc length parameterization. And so alpha here describes the angle. So what's happening is if this is the vertical axis, the curve gamma is winding around the vertical axis in circles of radius r and moving upward as it goes, etc. Okay, and so this is a curve. Okay, and so I can see that what does alpha mean? If alpha is 0, then we're just moving exactly in the vertical direction. If alpha is, as alpha goes to infinity, this would converge to something who doesn't move at all in the vertical direction, who's purely horizontal. And so alpha has to do with the angle of the helix. So as alpha increases, it wraps more tightly around the axis. Okay, let me. So this is just a smooth curve. Let me take the limits. Well, let me first draw a picture of the what's happening in S2. So this is the picture in R3. What are the tangent vectors doing? What the tangent vectors are doing is, well, the tangent vectors are always, I can see they always form a fixed angle with the vertical axis. The tangent vectors will have the form, alpha minus alpha sine and alpha cosine and 1 divided by 1 plus alpha squared. And so and so that means they'll be concentrated along a certain line of latitude. Like this, I think. So the tangent vectors, the typical vectors, alpha sine, alpha cosine 1 over 1 plus alpha squared. And so the dot product of the vertical vector is always, for example, 1 over 1 plus alpha squared. This is a if one is, and so as the curve over here wraps around, oops, didn't want that. Sorry, as the curve wraps around over here, the tangent vectors will rotate around here. And if r is small, so r is this distance, which and this distance is like r over alpha or something like that. It scales like this. If r is small, of course, we these wrap around more quickly. Jesus. Okay, so now I want to take the limit as r goes to 0. So let r go to 0. Okay, I'm having a hard time today with the technology. Okay, and so then in the limit, the curve will exactly converge to just a curve moving along the vertical axis. But the tangent vectors will, instead of being the vertical tangent vector, which is tangentless, the tangent vector will be exactly equidistributed around this line of latitude on the unit circle. Okay, and so the measure will be just the product measure of this measure living on the vertical axis in R3 and this uniform measure on this line of latitude in S2. And that's what I've written up here, I believe. So, and I've said, so I've done this a bit. I haven't done this carefully. I've done this in a hand waving style. But as R goes to 0, one can check that these measures in the top, the ones corresponding to the curves, the associated varifolds, converge to a uniform measure supported on the product of on the z-axis in R3 and in S2 this line of latitude. Okay, and so this is an example of a non-integral varifold, because if I have an integral varifold supported whose spatial support is the z-axis, then it's supported in S2, which is going to be will just be the tangent to this curve, and it's not. Instead, it's this line of latitude. And so here, the point of this oriented varifold is that this kind of captures the fact that the object I'm considering is a limit of highly oscillatory things. And so the structure of the varifold with this part who's diffused along a one-dimensional set above every point here, the corresponding tangent vector is not a single point, but is roughly is a larger set. The structure reflects the origin of this object as a limit of rapidly oscillating things. And so the point is that in principle, this formalism could be useful for studying, for example, solutions of the binomial curvature flow, or say limits of rapidly oscillating solutions of the binomial curvature flow. Okay, so these are examples of non-integral varifolds. So continuing, so here's then the definition of weak binomial curvature flow. So I'm going to give two definitions. We'll actually say very weak and then weak. And well, let me say another example of more examples of oriented varifolds would be the following. So it's just a measure. So things who are not integral, I could just take a bunch of curves and take their average somehow. You know, I could take well, one can write down very pathologic examples, things oriented varifolds who don't look at all like curves. Well, actually, this first example here does not look at all like a one-dimensional curve in general. It need not. Okay, and so when I write down very weak, those things need not look like one-dimensional curves, except in a very weak way. Okay, and then weak will have more geometric structure. And so a very weak solution is, well, I always want to impose two conditions. And so I'm always considering measures on R3 cross S2. So these oriented varifolds are the class of objects within which I'm working. I always ask them to be closed. I'm considering closed curves. And I always ask them to satisfy this identity, which is just, so here I've just taken the basic identity, which tells me how a binomial curvature flow acts on a test vector field. And I've rewritten it in the language of oriented varifolds. And so here, C is a proxy for the tangent vector. And so when I integrate this, I evaluate phi at the point x, and I take the dot product of it, and so sort of formally I'm taking the dot product of phi of x with the tangent vector. And on the right-hand side, I'm looking at this combination of second derivatives, and I take the dot product with the tensor product of the tangent vector with itself, which is exactly this is exactly the earlier identity rewritten in this new language. Okay, so this is, so the weakest definition of binomial curvature flow is this. I'd like to strengthen it in a couple of ways. So one is we can ask for it to have more geometric structure. So, okay, so this was very weak. It'll be weak if just, if it has more geometric structure, so it's integral. So it really, in this case, it looks like a bunch of Lipschitz curves. And then I want to add a crucial additional point, which is I would like to ask that okay, so I ask that, what's T sub 0? So what I mean here is no, sorry. Okay, so so I have this this T0 here. In general, I'll so you see if I and so here's okay. So when I have one of these oriented variables, I can always integrate out over the if I do this operation, then this defines a bounded linear function on vector fields on R3. And so where T naught is defined by this. So if I let my varifold act on on test functions this form, a vector field in X dot the vector C, then that gives me a measure on R3. So this is like taking the vector field, which is this object living in this product space, and start taking the varifold, a measure living in the product space, and projecting it down onto R3. That's what we're doing here. And so T0 denotes that projection. And T0 for an integral varifold, by definition, lives on a Lipschitz curve. Okay, so we're taking this kind of more abstract object and projecting it down to here where we see a Lipschitz curve. And then, and in general, I guess I'm defining T sub T, I should have. Okay, so in general, given this sort of abstract object, I can project it down into R3 where I see a bunch of Lipschitz curves. And so here I'm just sort of forgetting the thing up here, which explicitly records the tangent directions. Okay, and so so the second point, so then, let's see, I really need more space. Sorry. Let's go over this more slowly. So note, so given verified V, which is a measure on R3 cross S2, we can define a vector value measure T sub V on R3 by saying that the integral of phi of x dot d T sub V, or T sub V of dx we defined to be the integral of phi of x dot c dv of x and c. So here I'm integrating over R3 cross S2, and here I'm integrating over R3, and this is for all phi in C0. It doesn't really, I guess, I'm used to writing C infinity, but if I'm just integrating, all I need is continuity to integrate, for sure. Okay, and so this projects V onto R3. And so the interpretation is, so we'll, also, we interpret the measure V of R3 cross S as the total arc length. This is true in for the examples of Lipschitz curves, and it's also true in a sense for the above example. And so so in this highly oscillatory example, if I look at the total measure of a set, that would be the arc length in the set, and that would be the limit of the arc length of the oscillatory curves. And so in this example, this object would have arc length per unit. So it would have kind of a generalized arc length, or the verified mass would be larger than 1 per unit arc length in the sort of naive sense of the curve down here. Okay, so we interpret this as arc length, and this is equal to no, this is not always equal to, this is okay. So let me say a little more. Okay, another example of a sort of a fun example, or a trivial but important example of an oriented variable is this. So again, it's useful to think of an oriented variable as being a limit of sort of these slightly pathological objects as being a limit of smooth objects. And so one thing I can do is I can take, for example, two line segments. So the oriented variable corresponding to 2 line segments oriented in different directions at a distance r. And I can then let r go to 0, and I'll get a limiting object. And so the limiting object will be, it'll be a measure whose spatial support is this curve, and it'll have, and then when I look what's happening in S2, it'll be supported on 2 antipodal points, say the North Pole and the South Pole. And so when I then look at the when I look at this thing, the T sub V would be 0, because so T sub V would mean I integrate the vector field, I integrate both up the one curve and down the other curve, and so the 2 contributions cancel. But the verified V is not trivial. Okay, so one can have cancellation in the varifold. So the varifold records more stuff. It record the presence of these things before they cancel. And so that would be an example in which the total variation of the varifold, the generalized arc length, is bigger than the total variation of the projection down into arc3. Okay, so so anyway, the last condition here is that the generalized arc length at any so this here, this thing is the generalized arc length at any subsequent time t is less than or equal to the arc length at time 0. So at time 0, this would really be the actual arc length. By the way, this is how I want to imagine this. Okay, and so the point here is for very weak flow, we just ask these integral identities to hold. One says it's closed, and one says it satisfies the basic balance law. For a weak flow, we ask it to have this additional geometric structure, and then we ask that, roughly speaking, the arc length is never greater than its arc length at time 0. Let me give an example of so first, the first lemma is that, are there any questions? This may be a bit, so in a way it's just language, but it's, it may be a bit abstract if you're not used to this kind of language. So feel free to ask questions. And let me say the first lemma, which is that every weak binormal, if I have a smooth binormal curvature flow, then the family of associated measures of varifolds defines a weak binormal curvature flow. Because, well, definitely they're integral because they're varifolds associated to curves. We've noted that the arc length is constant for a smooth solution. And so in particular, it's bounded by its arc length at time 0. And then we've seen that, well, okay, smooth curvature is closed and it satisfies this identity. Okay. Let me give an example of a weak solution who is not a smooth solution. Well, I'll do that in a second. I think we have space for it down here. Okay, so then let me point out that, so in the definition of weak solutions, here's where the solution is this object V sub t. Here it is. Here and here and here to it appears in a linear way in the definition closed. So although the flow is highly nonlinear, in some way weirdly this V sub t appears linearly in the definition of weak solution. This should make us a little uneasy, but okay, so the last conditions aren't quite linear, but okay, and so then these very weak flows may in principle be useful for describing sequence of solutions with rapid oscillations. And then it's easy to construct examples of weak solutions exhibiting change topologies. Let me do that. So here's an example. Let's let be solutions of corresponding to, say, circles of radius 1 about the z-axis. Okay, here's a picture. moving toward each other. Okay, so remember the basic solution to the binomial curvature flow is just a circle moving with velocity given by 1 over its radius. And the direction in which it moves is determined by the orientation. And so if these curves are oriented in different directions, if they have the opposite orientations, then they'll move in different directions. And at a certain time they collide. And so then let V sub t be V of gamma 1 plus V of gamma 2 before the collision, and 0 after. Okay, and so here's the weak solution. Now, these two circles, they move, they collide, and then at a certain point, they annihilate each other. And they vanish, they disappear. Or if I like, they can sit there and stay there as a varifold with mass, with mass 4 pi, but with the two pieces canceling each other with opposite orientations canceling each other when I project down into R3. This is a perfectly good weak solution who's not a smooth solution. And this clearly exhibits change of topology. It goes from having 2 connected components to having 0 connected components. What this example illustrates several things. Well, actually, one thing is you can kind of see this in there are these amazing videos on YouTube of what happens if you aim 2 circles and you aim 2 vortex rings in water at each other, and they collide, and well, they don't exactly vanish, but they definitely annihilate each other. Okay, so that's something. Then let me remark the one of the conditions in the definition of weak solution was, so a condition in so mass, which is arc length, is not increasing. This isn't quite a, okay, mass at times non-zero times is bounded by the mass at time by the arc length times 0. This is needed because you see, if I didn't have this, we could run the above process. Backwards. So I would define V tilde T is V minus T. Maybe I need to change the sign of the tangents to do this. I think I do. Okay, and so this would be equals 0 for t less than some t naught, non-zero for t bigger than t naught. For t bigger than t naught, it would involve the 2 rings moving away from each other. And you see, if this is permissible, then I could have these pairs of vortex rings being born anywhere out of the vacuum and doing God knows what, or I could have more complicated others. There's no hope for a reasonable theory for, say, any kind of uniqueness or anything if I allow that to happen. If stuff can be born out of the vacuum and can cause trouble. And so this is the reason for this assumption. Why this assumption of mass non-increasing is really almost necessary for a reasonable theory. Okay, and so then quickly conserved quantities. And so the, okay, so what I'm doing here is I'm recalling some conserved quantities for the binomial curvature. Well, actually for the, well, the point was for the binomial curvature flow, this identity implied a bunch of conservation laws, which were essentially momentum and angular momentum. And so remember, momentum was the projection onto any two plane of the curve, the area enclosed by that projection. And angular momentum was a kind of angular counterpart of that, the projection onto any angular slice of the curve, the area enclosed, or the volume enclosed by that. Okay, so, and the point is that because those conservation laws depended only, were in fact derived by this identity, they're still going to hold for weak solutions. And so, so this P and Q, we derive them by taking specific choices of test vector fields, phi in that identity, who is the basis of the definition of weak solution. Right here it is. So P is exactly, has this form for a certain choice of the vector field phi, and similarly Q has the same form for a different vector field. And so these are formally conserved for the binomial curvature flow. And so this is what we actually did before. And let me remark that the honest binomial curvature flow has all these other conserved quantities: arc length, the L2 norm of the curvature, and then indeed this whole infinite hierarchy of conserved quantities because it's related to an integral equation. It can be transformed into the cubic non-linear Schrodinger equation by this Hashimoto transform. And so there are infinite hierarchy of conserved quantities. We can see right away that most of these will not be conserved for weak solutions because of the example I just gave, right? So here, if I have these two circles who are not at each other, well, arc length wasn't conserved. It's gone from being 4 pi to 0. L2 norm of the curvature is not conserved. None of that stuff is conserved. And so the only known conserved quantities for the weak solutions are these ones who come directly from the conservation law. And these involve vector fields phi, for which this quantity is pointwise antisymmetric. That was how we derived them before. Let's see, what time is it? It's getting late. Okay, so so I want to start deriving properties of this. And so the goal is to, eventually in a day or two, we'll return to the Euler equations. And what I want to do is first to derive a kind of a continuity property to show that these weak solutions are continuous in time in a kind of a way that actually is unsatisfactory in some senses. But we'll see that. And so to do this, I have to introduce a useful norm. And actually, this is interesting if you haven't seen it before. And so here I'm introducing what's called the flat norm, or the homogeneous flat norm. Let's highlight this. Okay, and so I should have emphasized this a bit more. And so when I say one current in R3, these are the, so this means that it's something who acts on smooth vector fields. And so this is the, so in particular, when I take this varifold and I do this projection operation down here, then I get, so one current, you can think of being a vector value measure. It acts on smooth vector fields. Okay, and so I've written a definition here. It's, so the definition makes sense for it doesn't, I don't require it to act on a difference of vector fields. It could act on simply a vector field. So I could define a flat norm for some mu, but it's a dual norm. And so it's a norm who's dual to, I look at the action of T on smooth complex Porter things whose curl is at most 1. And so if instead of the curl I had, say the, so this is, if instead of the curl I had the Lipschitz norm of the vector field, then that would make this a, let's see, if I strengthen this, that would weaken the corresponding dual norm, so well, let's say this is related to, so it's related to the W minus 1 Sobolev norm. Or the Lipschitz dual norm. If I had W minus 1, 1, I would have and if I had okay, so these are norms that may appear more natural from an analytic point of view. And so these are all dual norms, the flat norm and these other two related guys. And you can see that, well, for example, these two scale similarly. Here I'm looking at the L-infinity norm of all first orders. Here I'm looking at the L-infinity norm of certain linear combinations of first orders. And so this norm is certainly stronger than, so the Lipschitz norm is certainly stronger than the L-infinity norm of the curl. And the W1 infinity norm is still stronger because this involves control over both the gradients and the function itself. And so strengthening the norm on one side is the same as weakening the dual norm on the other side. And I can see the scaling in these two is the same, right? I'm looking at L-infinity norms of certain derivatives. And then here I'm making it a non-scale invariant space in the naturally non-Hermitians. Okay, so we're out of time, but what I'll show next time is that this flat norm has a very nice geometric interpretation. And this allows us to describe a natural continuity property of very weak solutions to the binomial curvature flow. Okay, so are there any questions about anything? And all this stuff may be a little bit, well, actually, let me do this. I've been terribly negligent about posting material and making material available, but let me put these notes in the chat if I can. Actually, so I'll, how do I do this? I'd like to upload these. I guess I have to go here. Let's do that. And then I can probably put them in the chat. And so this will include some material that I'm going to talk about next time as well. The next, say, 2 or more lectures. Okay, and so, okay, so if this is unfamiliar, then you can go over these notes at your leisure if that helps. Let me stick around for a while in case you want to download this, and also for questions if there are any. And so the general idea here is we're sort of, one doesn't, so this is if you like, a geometric measure theory approach to this question. So geometric measure theory is, somehow I find, I start saying the actual interesting and relevant things when the hour is over. I should have said this during the hour, but so geometric measure historically is this approach to geometric variation problems, like the minimal surface problem, that developed. Well, maybe I'll say this next time, but for say the minimal surface problem in particular, was found to be useful to have notions of a weak solution of the problem that so that in the same way that for elliptic PDE, it's useful to separate, or for any class of PDE, it's useful to separate existence and regularity questions, and so one can prove existence in the frame of weak solutions and then address regularity questions elsewhere, or separately, or they can be decoupled to some extent. This was also useful for geometric variation problems. And so certain classes of generalized surfaces were defined for minimal surfaces and so on. And here we're taking the same approach to this binomial curvature flow. And so this language of variables and so on was first developed in different contexts in this elliptic PDE, or this if you like, elliptic geometric setting. And here we're attempting to transpose it to geometric problems of a dispersive character, which is the character of this binomial curvature flow. And so that's the plan. And right. Okay, hopefully I'll be able to see on Wednesday.